All right, so we're in chapter 10, looking at correlation. So in this chapter, we're going to review several different types of correlations that you're likely to come across in psychological research. A correlation, it's a statistical measure that describes the extent to which two variables are related to each other. It quantifies the direction and strength of the relationship between variables, and it typically ranges from -1 to +1. Understanding correlation, it is crucial in psychological research as it helps researchers identify and interpret patterns and relationships within the data. So, we're going to look at scatter plots again and histograms. We did cover this back, as you remember, in chapter 5 when we were exploring data visualization. So scatter plots are a simple but effective tool for visualizing the relationship between two interval or ratio level variables. They are often used in conjunction with the most commonly used measure of correlation, and with Pearson's R, and we're going to learn about Pearson's R in the next section. So on the scatter plot, each observation corresponds to one dot, and the horizontal location of the dot plots the value of the observations of one variable, and then the vertical location displays its value on the other variable. So in many situations, you don't really have a clear opinion about what the causal relationship is. So does A cause B, or does B cause A? Or does some other variable, like variable C, control both A and B? So if that's the case, it really doesn't matter which variable you plot on the x-axis and which one you plot on the y-axis. However, in many situations, you do have a pretty strong idea which variable you think is most likely to be causal, or at least you have some suspicions in that direction. If so, then it's conventional to plot the cause variable on the x-axis and the affected variable on the y-axis. So we're going to go over again how to draw the scatter plot, and we're going to use the Parenthood data set. Okay, so let's take a look. So we grab our JASP, okay, and then we follow our directions. So we have our little hamburger here. And we're going to open up our data set. Of Parenthood. Right? And then, suppose our goal is to draw a scatter plot, okay, displaying the relationship between the amount of sleep that I got, right? Remember Danny's sleep and how grumpy I am the next day. So we would plot Danny's sleep versus Danny's grumpiness. And again, back in chapter 5, we saw 2 different ways that we could make the scatter plot using the JASP statistical software. So now we're going to actually look at the third approach, okay? And so let's look at the function we haven't used up until now. So we're going to look at regression. Okay, so we're going to select regression, and we have classical and Bayesian. So we're going to do the classical correlation. Okay. And then we're going to, again, move our Danny's sleep to the variables box, and we're also going to move the grumpiness variable to the variables box as well. And then we can go under plots. Okay, and we can check scatter plots. All right, so there's one beautiful illustration. So then we're going to check the output of 10.1. Okay, and so let's just double check the variables. So the one thing is they didn't display it pairwise, so they unchecked that. And then we reported significance, okay. And we have Pearson's R, which we're going to talk about next. It says that we're looking for correlated alternative hypothesis, right? Not a t-test. And we're doing the scatter plot. Okay, this is the first one, so this is our scatter plot, and then let's double check our values. So under grumpiness, we got a Pearson's R of negative 0.903, a p-value of less than 0.001. All right, and then if we check this, this scatter plot, it goes 4 to 9, okay, and then 40 to 100. Let me see one other thing. All right. And then in order to get the histograms to plot, we're going to check the box for densities, okay? So we'll check this. And then we see that we get our histograms. So this one here goes from 4 to 9 for Danny's sleep, okay? And then the one here is for the grumpiness, and it goes from 40 to 100, and it looks exactly the same, okay, as our chart. So let's keep going here. We're going from page 1 to page 2. So again, note that with the scatter plot in this JASP software, it draws a line through the points, okay, and by default this is a simple linear regression line, which we're gonna talk about more in the next chapter. And then the scatter plot we have shown here has a negative slope because as we move from left to right, the trend is downward. A negative relationship between grumpiness and sleep means that Danny tends to be grumpier on days when she gets less sleep and vice versa. The points on the scatter plot, they do tend to fall, they fall very close to the regression line, which tells us that the correlation is probably very strong, okay? So we can assign a numerical value to this relationship, right, of strength to the value. We can assign a numerical value to the strength of this relationship of our scatter plot, and this is where Pearson's R comes in. So Pearson's R, okay, as we saw right here, okay, Pearson's R for correlation coefficient. It's also known as the Pearson correlation coefficient, and it is the most commonly used measure of correlation, right, in, here we go. So it is the most commonly used measure of correlation in psychological research. It can be used when we have two interval or ratio level variables that have a linear relationship. So a linear relationship, again, is one where the line of best fit is a straight line. Pearson's R is a numerical value that must be between -1 and +1, where the R equals -1, indicating a perfect negative relationship, and if the R equals +1, that indicates a perfect positive relationship. So as with the Z and the T test that we saw in the last chapter, there are some assumptions that have to be met in order to use Pearson's R as a measure of correlation. So now we're going to go through those assumptions. So we're at the bottom of page 2. So again, we've already seen two assumptions of Pearson's R. The first is that both variables are interval or ratio level variables. Okay, so let's see. So let's say number 1, all right. Our assumptions, we have to have interval or ratio level variables. And some textbooks will say that both of the variables have to be continuous, but really Pearson's R, it can often be computed with discrete variables as long as the variable is interval or ratio level and has many different values. Second assumption is that the relationship between the two variables must be linear, okay? Okay. So if you were to look at a scatter plot and draw a line of best fit, that line should be a single straight line and not have a curve in it. So now we're moving to page 3. The third assumption here for Pearson's R is that both variables should be approximately normally distributed. Okay. Right. So there's our assumptions. Okay. Now, Pearson's R is relatively robust, and this means that it can handle some deviation from normality. However, before computing Pearson's R, it is usually a good idea to look at a histogram of each variable to ensure the distributions are not extremely skewed, that they're not bimodal, or anything else that would be extremely, different or that deviates from normality. Pearson's R, it can be greatly affected by outliers, so that's important to know. Again, outliers are the unusual data points that are much higher and much lower than the rest of your data. These outliers can make the correlation coefficient actually really misleading. To find outliers, you can use a histogram and the scatter plot. And a histogram can help you spot univariate outliers, which are the extreme values of just one of the variables. A scatter plot can help you identify bivariate outliers, which are unusual data points that don't fit the trend of the rest of the observations. So how an outlier impacts the correlation coefficient, it depends on its location. So coming up in another figure, in figure 10.2, if we compare scatter plot A with scatter plot B, then the addition of the outlier at 2 and 9 decrease, and the correlation coefficient from 0.832 to 0.392. This is also possible for an outlier to increase the correlation coefficient. So again, I'm just going to take a brief look at figure 10.2 here, and I can see that there's A, B, and C, and the value of scatter plot A, R equals 0.832, and B, the R equals 0.392, and in the third scatter plot, or scatter plot C, we have R equals 0.990, and again, going back here, we can see that in this figure with the 3 different pictures, if we compare the scatter plots like A and B, the addition of the outliers at 2 and 9, that is what decreased the correlation coefficient to make it 0.832 in A, and then it went to 0.392 in B. So then again, it is possible for an outlier to increase the correlation coefficient. So then again, in the same figure, we compared A and C, and the addition of the outlier at 30, 30 at that coordinate increased the correlation coefficient from 0.832 in figure A to 0.990 in figure C. But in either case, if we looked at a scatter plot, we could visually identify the outliers. And in general, it's bad practice to delete an observation just because it's an outlier. It is, however, acceptable to delete a data point if you believe it was entered erroneously. So for example, in 10.2c, if the x variable should never exceed 8, then we may have reason to believe that the outlier was just a human error of data entry, like someone typed 30 instead of 3. And then later on in this chapter, we'll learn about the other correlation coefficients that can be used when these three assumptions of Pearson's are or not met. Okay, so again, we have to have interval and ratio level variables. The relationship between the two variables has to be linear, right, on the scatter plot. And the third assumption is that both variables should be approximately normally distributed when you look at the histogram. Here's another summary on the bottom of page 3. So again, to review, these are the three things we should be looking for before we compute Pearson's R. So we have two interval or ratio variables that are either continuous or if they are discrete, they have many possible values. There is a linear relationship between the two variables, and we check this by constructing that scatter plot. Both variables are approximately normally distributed, and we can check this by making the histograms. They do not need to be perfectly normal, but they should not be heavily skewed or bimodal, etc. And there are no extreme univariate or bivariate outliers. So on our scatter plot and histograms, we can look for values that don't fit with the general trend, and then we can identify an outlier. When we identify an outlier, we question if it's valid, if it's a valid observation, or if it was like a data entry error, okay? So we're gonna actually add that here. We're gonna make a number 4. So we're gonna say no extreme outliers. Save. Okay. Looks good. So if these assumptions are all met, then we can use our Pearson's R. We're at the bottom of page 3. If any of these assumptions are not met, then we need to consider some other options, but we're going to talk about those options later in the chapter. We're going to move into page 4, and again, we're going to do some more practice on the parenthood example. So throughout this section, again, we're going to continue to use this data set, the parenthood data set, in example forms. So this example uses a topic close to every parent's heart, right? Sleep. The data set, it is fictitious, but it is based on real events. So suppose I'm curious to find out how my infant son's sleeping habits are related to my mood. So let's say that I can relate my grumpiness very precisely on a scale from 0, which means not at all grumpy, to 100, which is maximal positive grumpiness, maximum possible grumpiness. So let's also assume that I've been measuring my grumpiness and my sleeping patterns and my son's sleeping patterns for quite some time now. Let's say for about 100 days, okay? And you know, being a nerd, I've saved this data as a file, again, called Parenthood. And if we load the data into this statistical software, JASP, we can see that this file contains those 4 variables, right? So let's go back here. Right, so we had all of these variables, and we'll put this back. Okay. So here we are. So after we loaded this data set, we see Danny's sleep, baby's sleep, Danny's grumpiness, and we see the day, and we see a random ID. Okay. So note that when you first load this data set, the statistical software JASP may not have guessed the data type for each variable correctly. So in which case you should then go fix it and make sure that your variables like Danny sleep, baby sleep, Danny grump, and day are all listed as scale, and then you want to make the this one, okay, we're gonna go back here and we're gonna open up the file again, okay. So there we go. And see up here, this one is actually nominal. It's not a scale variable. So we double click and then we change this to nominal. Okay. And again, we can run our descriptive stats. Or we could go into regression or whatever. But let's say we wanted to do Danny's sleep and Danny's grumpiness. So we can see here the mean sleep again for these 100 values was almost 7 hours, and the grumpiness from 0 to 100 was on average about 64. We see our standard deviations, our min and our maxes for this data set. And so let's keep reading this. So again, these 3 variables that we're going to use for our correlational analysis is going to be Danny sleep, baby sleep, and Danny grump. So let's add baby sleep here too. again, these are all interval and ratio level variables, right? And next, we're going to take a look at some basic descriptive statistics and then give the graphical depiction of what each of the three interesting variables looks like. So let's make sure we again have it as they set up here. So they actually put my grumpiness first, okay, and then they did my sleep, and then they did the baby's sleep. That's how they set it up in that order. So my grumpiness, my sleep, and the baby's sleep, and we're going to plot histograms. So as we remember, we can go under distribution plot, okay, and that'll make the histograms. So let's check. Yep, looks good. Okay. So again, we're taking a look at some of the basic descriptive statistics to give the graphical depiction of what each of the three interesting variables looks like, and it's plotted in figure 10.3, but it's also plotted right here because we just did it. So all three histograms are close enough to normal that we are comfortable moving forward. But let's check display density, because it'll draw the line on there for you if you remember. See? So it looks pretty close to normal. Not anything too crazy, right? Not a perfect bell curve, but not too far from normal. So one thing to note again is just because JASP can calculate dozens of different statistics, it doesn't mean that you should report them all. So if I were writing this specific example for report, I just pick out the statistics that are most important to me and to the people reading my data set and reading my results. So, and then I put them into a little table, like maybe this type of a table here, where we have, again, we could use this descriptive stats table where we can see the mins and the max, the mean, the standard deviation. We could even add like interquartile range if we wanted, right? We could check IQR. And there it is. So then we can see the IQR is 14, 1.45, and 3.21. So as we see, Danny is not getting the recommended 8 hours of sleep. And again, as most parents know, right, it's not a good practice to get less than 8 hours, but you know, it's pretty standard when you're a new parent to not get very good sleep. So now we're at the bottom of page 4. So we can draw scatter plots again to give us a general sense of how closely related each pairing of variables is, and ideally, though we might want to say a bit more about it than that, for instance, let's compare the relationship between Danny's sleep and grumpiness. So on the left side of figure 10.4, we can see Danny's sleep versus grumpiness compared to baby's sleep and Danny's grumpiness on the right. So when looking at these two plots side by side, it's clear that the relationship is qualitatively similar in both cases, right? So more sleep equals less grumpy. However, it's also pretty obvious that the relationship between Danny's sleep and Danny's grumpiness is stronger than the relationship between baby's sleep and Danny's grumpiness. So again, we're moving on to page 5, and we can see that the plot on the left is a lot neater than the one on the right. So what it feels like is that if you want to predict what Danny's mood is, it'd help a little bit to know how many hours that Danny's son, the little baby, slept, but it'd be more helpful to know how many hours that Danny slept, right? So again, here's some scatter plots that are showing on page 5 the relationship between Danny's sleep and grumpiness, and then in the other scatter plot, it's the baby's sleep and Danny's grumpiness. So in contrast, we're going to consider the two scatter plots that are also shown in figure 10.5. So if we compare the scatter plot of baby sleep versus Danny's grumpiness, right, to the scatter plot of baby sleep and Danny's sleep, so A and B, the overall strength of relationship is the same, but the direction is different. So this means that if Danny's son sleeps more, Danny gets more sleep. That's the positive relationship on the right-hand side. If the baby sleeps more, and Danny gets less grumpy, that would be the negative relationship on the left-hand side. So again, to review, we were on page 5, looking at figure 10.5, looking at these scatter plots that are showing the relationship between the baby's sleep and Danny's grumpiness, right, on the left, and then comparing that to the baby's sleep and Danny's sleep on the right. So we can make these ideas a bit more explicit by introducing the idea of the correlation coefficient. So in this section, we're going to focus on the one specific correlation coefficient, which we just talked about, Pearson's R. The correlation between two variables x and y is sometimes denoted as little r xy. When referring to a correlation in a population, the Greek letter rho, RHO, or little p, is sometimes also used. Now we're going to move to page 6. Page 6 has quite a few representations of Pearson's R. Okay, so in this figure 10.6, we can see illustrations of the effect of the varying strengths and directions of the correlations. So on the left-hand column, the correlations go from 0 to where that's no correlation to 0.33 to 0.66 to 1.0. In the right-hand column, we can also see that there would be 0, and then a negative 0.33, negative 0.66, and negative 1.0. We're going to move on to page 7. All right. So again, we're going to be talking about some math now. But we're going to be still talking about Pearson's R. We're going to go through, so you can refer to your textbook, page 7. You can go through that to see this math that we talk through really quick. So Pearson's R, it's a measure that varies from -1 to 1, where R equals -1, which means we have a perfect negative relationship. And when R equals +1, it means we have a perfect positive relationship. So when R equals 0, then there's actually no relationship at all. If you look in figure 10.6, we'll be able to see several plots that show the different correlations and what they look like. Note that the numerical value in the correlations communicates strength and the sign communicates direction, positive or negative. So in the correlation R equals -0.90, that would be a stronger correlation than a correlation of R equals +0.50. For the formula for the Pearson correlation coefficient, again, this is on page 7. And it can be written in several different ways. I think the simplest way to write down this formula is to just break it up into 2 steps. Firstly, let's introduce the idea of a covariance. The covariance would be abbreviated by COV, and this would be between variables x and y, and it's a generalization of the notion of the variance and is a mathematically simple way of describing the relationship between 2 variables that isn't terribly informative to humans. So we can see a pretty long and complicated equation right there on page 7. Because we're multiplying, right, we're taking the product of a quantity that depends on x by a quantity that depends on y, and then averaging, you can think of the formula for the covariance as an average cross product between x and y. The covariance has the nice property that if x and y are entirely unrelated, then the covariance would be exactly 0. If the relationship between them is positive, right, as we see in figure 10.6, the covariance is positive. If the relationship is negative, then the covariance is negative. In other words, the covariance captures the basic qualitative idea of correlation. Unfortunately, the raw magnitude of the covariance isn't easy to interpret, as it depends on the units in which x and y are expressed. Worse yet, the actual units that the covariance itself is expressed in are really weird. For instance, if x refers to the Dan sleep variable in the units of hours and y refers to the grumpiness of Danny, and that variable is in grumps, then the units for their covariance are hours times grumps. And I have no idea what that would even mean, right? So the Pearson's R then fixes this interpretation by standardizing the covariance in pretty much the same exact way that the z-score standardizes a Ross score by dividing by the standard deviation. So, however, because we have 2 variables that contribute to the covariance, the standardization only works if we divide by both standard deviations. So in other words, the correlation between x and y can be written as little r subscript xy equals COV x comma y, and then the estimated x times the estimated y. Again, that equation is in the middle of page 7. So by standardizing the covariance, we do not only do we keep all of the nice properties of the covariance that are discussed earlier, but the actual values of R are on a meaningful scale. So R equals 1 implies that perfect positive relationship. R equals -1 implies a perfect negative relationship. So I will expand a little bit more on this point later. So in section 10.2.4, before we do that, we're going to look at how to calculate correlations in JASP and test for the statistical significance. So in addition to computing the Pearson's R for us, the JASP will also test for statistical significance. By default, JASP will compare the correlation to a population parameter of 0. The default hypothesis that JASP will use when testing the statistical significance of Pearson's R are as follows. So the null hypothesis equals 0, and the alternative hypothesis is that it does not equal 0. And the pxy in this equation is the correlation between x and y in this population. The sampling distribution used to test these hypotheses is one that we've seen before. It's a t-distribution with n-2 degrees of freedom. The standard error is computed as SE of little r is the square root of 1 minus r squared divided by n-2. Again, that is at the bottom of page 7. Here's a few subscript notes. So just like we saw with the variance and the standard deviation in practice, we usually divide by n-1 rather than n. Another subscript 4 at the bottom of page 7, it does remind us that that was an oversimplification, but it's going to be okay for the purposes of introductory statistics and learning about correlation. And the subscript 5, bottom of page 7, in JASP under alternative hypothesis, you're going to see the default setting is labeled as correlated. So use this if you're conducting a two-tailed test. And if you do have the option to change this to correlated positively or correlated negatively, you can do that if you would like to conduct the right-tailed or the left-tailed test. We're going to move on to page 8. So the formula for the test statistic will follow the same general structure that we saw with the other t-tests in the last chapter. It's going to be that fraction with the same test statistic formula. So we have r in the numerator divided by the square root of 1 minus r squared over n-2, and that would give you your sample t-test statistic. So we're not going to worry about the, doing the math by hand again. We're just going to allow JASP to do it for us. And now we're going to do our example and follow the instructions on page 8. So let's do that. So we're gonna redo it. Okay, we're gonna close these. All right, so there's our original. Here we go. So let's start with, again, our easy example. We're going to compute the correlation between two variables of Danny's sleep and Danny's grumpiness. So again, we see that our scatter plot is shown, and so we have Pearson's R is calculated like before. We're reporting significance, so we have a p-value, right? So it's significant. And then under additional options, we have the box checked display pairwise if we want to, or we can display it this way. So we're going to try it the alternative way for now. All right. And it makes it more condensed. And then optionally, under additional options, you could check the boxes next to confidence intervals and sample size. Okay. So again, we're going to compare the results in figure 10.7 here. So it looks the same, right? We have n equals 100, Pearson's R, negative 0.903, p-value less than 0.001, 95% CI, negative 0.934, negative 8.59, 95% CI. So from this, from figure 10.7 that we just went over, which is our Pearson's correlation up here, we can confirm that our sample size is 100. The correlation between Danny's sleep and Danny's grump is negative 0.903, which signifies a very strong negative relationship. Okay. The p-value is less than 0.001, which tells us to reject the null hypothesis. There is evidence of a relationship between these variables in our population. The 95% confidence interval for the correlation in the populations is open bracket negative 0.934, comma, negative 0.859, close bracket, which means we are 95% confident that in the population of all possible nights, that the correlation between how much sleep Danny got and how grumpy Danny is between R equals negative 0.934 and R equals negative 8.59. Again, in the example shown here, only two variables were selected. So what happens if we select more than two? So let's say we do that and we add baby sleep. Okay. So let's add this one, which is our third value. And now we're looking at our change in our correlation results in JASP on the computer screen. And I'm also comparing the data output to page 8. So now instead of having one correlation, we have 3 correlations. JASP is computing every possible two-way combination of variables. So when we added baby sleep here, we got this third row. Okay. Moving to page 9. So when we're looking at multiple correlations, it is common to use a correlation matrix. A correlation matrix is a table that displays the correlation coefficients between multiple pairs of variables. So correlation matrices are particularly useful for identifying patterns and relationships among several variables simultaneously. They help researchers to quickly assess which variables are strongly or weakly correlated and positively or negatively correlated. So how do we do it, right? So in order to make a correlation matrix using these three variables, we go to regression. Again, we're in classical and we select correlations, and then we move all three to the variables box, which we did, right? So we already have done this correlation. We've moved everything Danny's sleep, grumpiness, and baby sleep. Okay. And we can display it in a different way, okay? Instead of doing the display pairwise, we can illustrate the data this way. Right, so let me go here. And we can check sample size. Okay, so then we get our, like Danny's sleep, then we get Danny's grump, and then we get baby sleep, and everything matches. And so if we're on page 9 and we're looking at 10.9, we get the same output that we got in our JASP demonstration. And this is known as a correlation matrix using three variables. So each row and column of the matrix represents a variable. Each cell shows the sample size, Pearson's R, correlation coefficient, p-value for the correlation between the variables corresponding to that row and column. So for example, in figure 10.9, which we can see on our screen here, to find the correlation between Danny's sleep and Danny's grumpiness, we find the column labeled Danny's sleep and the row labeled Danny's grump, okay? And at that intersection, we find a correlation of R equals negative 0.903, as well as our sample size of 100, p-value less than 0.001, okay? So now we're at the bottom of page 9, and we're going to go briefly through again, how do we interpret Pearson's R. So how do we interpret it? Page 9, bottom. So naturally in real life, you don't see many perfect correlations of 1. So how should you interpret a correlation of, say, R equals 0.4? The honest answer is that it really depends on what you want to use the data for, and it also depends on how strong the correlations in your field tend to be. So like a friend of the author's is in engineering and once argued that any correlation less than 0.95 is completely useless. The author of this text believes that the engineer friend was exaggerating even for engineering. But on the other hand, there are actually real cases, even in psychology, where you should really expect correlations that strong. For instance, one of the benchmark data sets to test theories of how people judge similarities is so clean that any theory that can't achieve a correlation of at least 0.9 isn't deemed to be successful. However, when looking for, let's say, elementary correlates of intelligence like inspection time, response time, if you get a correlation above 0.3, then you're doing pretty well. We do have a rough guide on the next page in table 10.2, and it's pretty typical. However, something that can never be stressed enough is that you should always look at the scatter plot before attaching any interpretation to the data. A correlation might not mean what you think it means. We're moving to page 10. The classic illustration of this is Anscombe's quartet, which is a collection of 4 data sets. And each data set has 2 variables, x and y. For all the data sets, the mean value of x is 9, and the mean value for y is 7.5. The standard deviations for all x variables are almost identical, as are those for the y variables. And in each case, the correlation between x and y is r equals 0.816. You can verify this yourself since we do have a file saved as anscombe.csv. You'd think that these 4 data sets could look pretty similar to one another, but they don't. So if we draw scatter plots of x against y for all 4 variables as shown in figure 10.10, we then see that all 4 of these are spectacularly different from one another. And the lesson in this example is that always graph your raw data, and a lot of people seem to forget to do that in real life. So the next topic is going to get into the coefficient of determination. So let's see. We're going to add a few notes on this slide. So we have Anscombe. You can look at that data set. Oops. Anscombe. We have the note, always graph your we're going to look at the coefficient of determination. Oops. Okay, let's take a look here. So we're on page 10. So the section 10.2.5, coefficient of determination, it's denoted as R squared, big R squared or little r squared. It's often thought of as a measure of effect size for Pearson's R. So R squared quantifies the proportion of the variance in one of the variables that is predictable from the variance in another variable. So when discussing Pearson's R, the coefficient of determination, it is simply the square of the Pearson correlation coefficient. This measure provides insight into the strength of the relationship between two variables by indicating how much of the variability in one variable can be explained by the variability in the other. Okay, so let's say that again. So we're looking at number 3 here, coefficient of determination, which is R squared, big R squared or little r squared. It's often thought of as a measure of effect size for Pearson's R. So R squared, again, it quantifies the proportion of the variance in one variable that is predictable from the variance in another variable. So when you're discussing Pearson's R, the coefficient of determination, it is simply the square of the Pearson correlation coefficient. This measure provides insight into the strength of the relationship between the two variables by indicating how much of the variability in one variable can be explained by the variability in the other. So as an example, in the correlation between Danny's sleep and baby's sleep, that was calculated to be negative 0.628. So let's do this. Danny's sleep and baby's sleep. I'm sorry. It is R equals 0.628. Okay, so we just had to revise how we ran the data, which one was first and which one was second. So we see n equals 100 here. We have Danny's sleep versus baby's sleep. Pearson's R equals 0.628, and it is significant, so we would reject the null hypothesis because our p-value is less than 0.001. Now, so then, if we take that a step further, the coefficient of determination would then be this 0.628 squared. So R squared equals 0.628 squared, which comes out to 0.394. This means that if we move the decimal 2 places, 39.4% of the variances of the variance in Danny's sleep can be explained by variance in the baby's sleep and vice versa. So remember that a negative number squared will be a positive number. And for example, the correlation between Danny's sleep and Danny's grumpiness. So let's do that one. So the correlation between Danny's sleep and Danny's grumpiness is R equals negative 0.903. So to calculate that coefficient of determination for this relationship would be r squared, which would be in parenthesis negative 0.903 squared equals 0.815. This means that if we move the decimal place 2 to the right, 81.5% of the variation in Danny's sleep can be explained by the variance in Danny's grumpiness and vice versa, okay? So if Danny's sleep was low, right, that would correlate to her being more grumpy. So in psychological research, the coefficient of determination, it is particularly useful when you're interpreting the results of correlational analyses. So we also will see it again in the next chapter when we learn about regression. The strength of the relationships they are studying. Let's see, hold on. We're going to back up here. So in psychological research, again, that coefficient of determination, the r squared, it is particularly useful when you're interpreting the results of correlation analyses. So we also will see it again in the next chapter when we get into more about regression. The coefficient of determination allows psychological researchers to quantify the explanatory power of their models, okay, and to assess the strength of the relationships in which they are studying. So while Pearson's R indicates the direction and the strength of the linear relationship, R squared, or the correlation of determination, okay, the coefficient of determination, R squared provides a more intuitive understanding of how much of the variability in the outcome variable is accounted for by the predictor variable, which makes R squared a really valuable tool when you're communicating your practical implications of your research findings to your audience. So let's go through that just one more time because that's like really important. So when you're doing specifically psychological research, the coefficient of determination, it is particularly useful for interpreting the results of correlation analyses. So we also will see it again in the next chapter when we go over regression. The coefficient of determination, okay, the R squared, allows researchers to quantify the explanatory power of their models and assess the strength of the relationships that they are studying, while the Pearson's R indicates the direction and the strength of that linear scatter plot, right? Well, this R squared, the coefficient of determination, or the R squared, again, is providing a more intuitive understanding of how much of the variability in the outcome variable is accounted for by the predictor variable, making R squared a valuable tool in communicating the practical implications of research findings to your broader audience, okay? And this last part we're going to look at, and then we're going to take a pause, is bottom of page 10, 10.2.6. So how do we report Pearson's R in APA style? So here we go. So just one last thing before we move on from Pearson's R to the other less commonly used correlations is how do we summarize the results of a correlational analysis in APA style, right? So if you have computed 3 or more correlations and then you need to report your findings, it's common to report your results again in that APA format, right? And you can do it in the table. If you are presenting 1 or 2 correlations, you can report the numerical value of Pearson's R along with the degrees of freedom and the p-value. The degrees of freedom for Pearson's R is computed as n minus 2. This also, it's also common to describe the correlation in terms of its direction and strength. So you may also see coefficient of determination reported. Though it is often left off because it is easy to compute from Pearson's R. Here is an example of how we could report the results of the analysis between Danny's sleep and baby's sleep. So let's do that. So actually, I think that might be a typo in the book. I think that's grumpiness, actually. Yeah, so let's report this finding. We're actually just comparing Danny's sleep to Danny's grumpiness. So we see our Pearson's R is the negative 0.903. So we could say there was a strong negative correlation between the number of hours of sleep, the number of hours that Danny slept, and the number of hours or we could say, and the level of, and the level of grumpiness Danny reported. So we have to factor in a little bit of error right here. So if we are using this book example, let me make the correction here. Because Danny's sleep and Danny's grump had a negative correlation. So let's just change what the output says. So there was actually here a positive correlation. So there was a strong positive correlation between the number of hours that Danny slept and the number of hours that Danny's baby slept that night. So for this example, it would say R 98 equals 0.628 P, comma P less than 0.001. So that would need to be adjusted. I see that typo. All right, now we're going to talk about Spearman's row.